This topic is on projection geometry. The contents include definition, principles, image sharpness and resolution, image size distortion, image shape distortion, paralleling and bisecting angle technique, object localization, eggshell effect. So what is projection geometry? It pertains to the source of X-ray beam and relationship between the X-ray beam and the structure being radiographed and the position of the X-ray film. So this is the structure being radiographed and this is the X-ray film and this is the X-ray beam. So let us see the principles of projection geometry. The first is focal spot size should be as small as possible. So here is the focal spot, it should be as small as possible, and the source and the tooth distance should be as long as possible. So that is the reason we say that long cone technique is better when compared to a short cone technique. Next, the tooth film distance should be as small as possible. So the film has to be kept as close as possible to the teeth. And next principle is that the long axis of the tooth and the film plane should be parallel to each other. So can you see this? The long axis of the film will be parallel to the long axis of the tooth. Next, the X-ray beam should be perpendicular to the tooth and the film. So this is the X-ray source. So it is at a perpendicular angulation to the tooth as well as to the film. Next, there should not be any movement of the tube, film or the patient. So we were discussing about certain distances in the previous slide. Let us see about that now. So target surface distance, it is the distance from the target to the surface, skin surface. Next is the target object distance, that is the distance from the target to the object, that is the teeth which is being imaged. Next is the target image receptor distance, that starts from the target to the image receptor. Image receptor is nothing but your IOPA film. Before going in detail with the principles of projection geometry, let us see about image sharpness and resolution. So what is image sharpness? It is boundary between two areas of different radio density which is revealed, and image resolution is nothing but how well a radiograph can reveal small objects that are close together. So there are three means to maximize the image sharpness. One is to use a small or effective focal spot as practical. Then increase the distance between the focal spot and the object by using a long cone technique. Then minimize the distance between the object and the image receptor. So starting with the first principle, use a small effective focal spot size as practically possible. So let us compare these two pictures. So this is the target and this is the image receptor and this is the unsharpness revealed. So the target, which has an actual focal spot size of 1:3, and this is a target which has 20-degree angulation with the long axis of the electron beam, and the actual focal spot size becomes effective focal spot size, which is 1:1. And now we'll compare the unsharpness. The target, which is angulated at 20-degree, has a less unsharpness, that is the image is very clear and it is more sharp when compared to the target which is placed having an actual focal spot size of 1:3 and the unsharpness is high, which is not expected for a diagnostic radiograph. So the effective focal spot size to be kept as minimum to increase the sharpness of the image. So the second principle is increasing the distance between the focal spot and the object using a long open-ended cylinder. So let us compare these two pictures. So the distance from the target to the object is shorter here, and the distance from the target to the object is longer in the second picture. Then let us compare the unsharpness. So unsharpness is more in the shorter cone when compared to the longer cone. So increasing the distance between the focal spot and the object results in an image with increased sharpness and less magnification. So for intraoral X-ray units, the distance from the source to the edge of aiming ring ranges from 8 inches and 16 inches, and that is how it is named as short cone and long cone. Next, minimize the distance between the object and the receptor, image receptor. So the decreasing the distance between the object and the film distance increases the sharpness and results in less magnification of the object. So here in this picture, the distance from the object, that is the teeth, to the film is less, whereas in this picture the distance from the object to the film is quite lengthier. And now compare the unsharpness here. We could see more of unsharpness in this image where the film which is placed away from the object. So minimize the distance. Try to keep the distance less between the object and the film image receptor. Next is image size distortion. Image size distortion, that is magnification, is increase in the size of the image on radiograph compared with the actual size of the object. So increase in focal spot to image receptor distance and decreasing the object to image receptor distance will minimize the image magnification. So the use of long cone as an aiming device on an X-ray machine thus reduces the magnification of the image on the periapical view. Next is image shape distortion. Image shape distortion is the result of unequal magnification of the different part of the same object. So this situation will come when not all the part of the object are at the same source to object distance. So let us see how to minimize the shape distortion. So if you want to minimize the shape distortion, the image receptor should be placed parallel to the long axis of the teeth. So if it is not placed parallel to the long axis of the teeth, what will happen? So in this scenario, we can see the teeth here, there is the object and the image receptor. We can see that the image receptor is not placed parallel to the long axis of the teeth. So what will happen then? So now when you expose the teeth, what happens? The X-ray beam will be placed perpendicular to the image receptor, but the object will not be parallel to the image receptor. So this will end up in a image distortion and will lead to foreshortening. So in short, foreshortening of a radiograph will result when the X-ray is perpendicular to the film and when the object is not parallel with the film. So to rectify that, what we have to do is that we need to position the image receptor parallel to the long axis of the object. Thereby, when the exposure occurs, the X-ray beam will be perpendicular to both the object as well as the film. So next is the X-ray beam is oriented at a right angle to the object but not to the image. So in this picture, we can see the target, the X-ray beam, the object, that is the teeth, and the image receptor. Here the central beam is perpendicular to the teeth, but the film is not placed parallel to the tooth. So what happens? It can end up in a image distortion resulting in elongation. So the image shape distortion occurs if the object and the image receptor are parallel, but the central ray is not directed at a right angle to each other. So this distortion is most evident on a maxillary molar view, where the divergence of buccal and palatal roots precludes placing all roots parallel to the receptor, and the palatal roots appear disproportionately longer than the buccal roots. So orient the central ray perpendicular to the object and the image receptor. So like this, the X-ray beam is perpendicular to the object as well as the image receptor. So image shape distortion occurs if the object and the image receptor are parallel, but the central ray is not directed at right angle. So this type of distortion is most evident on the maxillary molar, which I have already told. Paralleling angle technique and bisecting angle technique. Paralleling angle technique. This technique seeks to minimize the distortion by placing the image receptor parallel to the long axis of the tooth and direct the X-ray beam perpendicular to both the long axis of the teeth and the long axis of the image receptor. Bisecting angle technique. So this is the long axis of the teeth and this is the long axis of the image receptor. So this forms an angle and we need to draw an imaginary bisector in between the long axis of the teeth and long axis of the image receptor, and the central beam is directed at a perpendicular direction with, with the image bisector. So this method results in an image that is the same length as that of the original object. So let us see about object localization now. The three methods are frequently used to obtain three-dimensional information. So first is to examine two images projected on right angle to each other, so which you can choose an IOPA and an occlusal view. So the IOPA reveals in this picture, it shows an impacted canine in the mesodistal and the superior inferior dimension, and the maxillary occlusal radiograph provides an information in the mesodistal and the buccolingual dimension. So we get to know that the supra-inferior position of the canine is somewhere around the periapical region of the lateral incisor, and the occlusal view will show whether it is placed buccally or lingually and also shows the mesodistal dimension. So next is tube shift technique. So this technique is otherwise known as Clark's rule or slop technique. Slop is nothing but same side lingual and opposite side buccal. So let us look into this picture. In figure A, this is the first radiograph made with the central beam directed directly at a perpendicular direction to that of the premolar, and this is the resultant image where we could see this foreign body. The white dot is the foreign body. We could see the foreign body image just placed at the periapical region of the second premolar. So next is the figure B. Here the image is made with the central beam directed from the mesial direction. So this is the resultant image and we need to analyze the location of the foreign body. So we could see the foreign body which is placed between the first and the second premolar. So the inference is that the foreign body has moved towards the direction of the movement of the tube head. That is, it is moved mesially. So it means that same side lingual. So it is the foreign body is placed lingually. That is why it has moved along the direction of the tube head. So if suppose the same foreign body is placed buccally, what happens? So we'll see here, this is a figure A. So the first image is made by directing the X-ray beam perpendicular to the premolar, and this is the resultant image. We could see the foreign body which is placed at the periapical region of the second premolar. Now the tube head is shifted mesially and the X-ray beam is directed in a tangential way, in an angulation to that of the premolar. So the tube was shifted mesially and this is the resultant image. So the resultant image shows that the foreign body is present between the premolar and molar in the second X-ray. So the inference is that since the foreign body has moved away from the direction of the tube head, because in this image the tube head is shifted mesially and the second X-ray is made. The resultant image shows that foreign body has moved distal to the premolar. So it is placed between the second premolar and the molar in the second image. So it means that the object has moved away from the X-ray source. So it says that the object is placed buccally. So this technique determines the position of the impacted teeth, the presence of foreign body, and identification of multiple canals. So the third technique is that three-dimensional imaging technique. So now we have CBCT, which will give various images in various sections like axial, coronal, and sagittal. So it becomes easy for us to diagnose the position of the impacted teeth or the foreign body with a 3D image. So this is a CBCT taken, and this is a sagittal section which shows a mesioangular impaction of the molar. It also shows the relationship of the canal to the roots of the impacted molar, and this is the coronal section, which also reveals the position of the inferior alveolar nerve canal with that of the root apex. So we'll see about eggshell effect. So the image that projects three-dimensional volume into a two-dimensional receptor may produce eggshell effect of corticated structure. So here we have an example. The picture A, it is a radiograph of a hard-boiled egg. So we can see that the peripheral rim, the eggshell is opaque, even though the eggshell is uniform in thickness, because all throughout the shell, the thickness of the shell is going to be the same, but we could see that the periphery alone shows a rimming. So what is the reason? So egg being exposed to the X-ray beam, the top surface, the photon will travel in a tangential path through the apex of the egg, and it takes a longer path through the shell of the egg when compared to the lower photon. As a result, the photon traveling through the periphery of the curved surface are more attenuated than those traveling at a right angle to the surface. So here, can you see that the distance is very small? Okay, whereas when it travels at the curved surfaces, it has to travel a longer path. So the X-rays get attenuated, giving a peripheral rimming effect. And this is nothing but your eggshell effect. The picture C shows an expansile lesion on the buccal surface of the mandible on an occlusal view. So this is the occlusal view. So we can see some ballooning of the cortex. So the periphery of the expanded cortex is more opaque than the region which is inside the expanded border. That is result of a peripheral eggshell effect, which I had explained in the earlier slide. This is the reference for the topic. And thank you for patient listening.